Welcome to the Explainer. So today we're going to tackle a question that's right at the heart of how neural networks actually learn. You've definitely heard the term backpropagation, right? But today we're going to solve the mathematical mystery of where that backwards part really comes from. All right, let's dive in. Okay, so to get started, we've got to really understand the problem we're trying to solve here. When we train a network, it's all about figuring out how much to tweak each weight. We call that the gradient. But here's the thing. How we calculate that gradient totally changes depending on where in the network that weight is. Now, you'd think calculating this change would be the same for every single weight, right? But it's not. For a weight in that final output layer, well, that's pretty straightforward. It directly affects the final error, so the math is simple. But what about a weight that's buried deep inside the network? Well, that's where it gets complicated. Figuring out its tiny impact on the final result becomes a huge puzzle. So why is it so easy for that last layer? Well, it's because its outputs, its activations, are the ones we use directly to figure out the network's final error or loss. That connection is immediate, You can see exactly how tweaking that activation changes the final score. But for an inner layer, whoa, that's a whole different ballgame. Its activation doesn't get anywhere near the loss function directly. Nope. It has to travel through all the other layers that come after it, getting changed and transformed at every single step before it can finally have some kind of effect on the error. And it's this indirect, tangled path that makes the math so incredibly tricky. So the big question is, how do we solve for that really tricky part of the equation? Well, the only way is to trace the influence of that inner neuron forward through the network. But, and this is the crazy part, to do that, we actually have to work the math backwards from the final loss. Okay, so the key insight, the real aha moment, is realizing that the final loss isn't just one simple calculation. Think of it like a set of Russian nesting dolls. It's a huge, nested function. A function of a function of a function, all stacked inside each other, going all the way back through the network. And to figure out how one thing changes another in a setup like that, you need a very special tool from your calculus toolbox. And that special tool is the chain rule. This is our hero. It's basically the key that lets us carefully unpack those nested dependencies one layer at a time. It lets us trace how one tiny change deep inside the network creates ripples that spread all the way to the final output. So when we actually apply the chain rule, something really fascinating happens. It turns out, to figure out how just one of those inner neurons affects the final loss, you can't just follow one straight line. No way. You have to trace its influence as it spreads out to every single node in the very next layer. Then you have to add up all those individual little pathways of influence. It's not a single path, it's a web. Okay, so after all that math, after we apply the chain rule to untangle that messy, tricky term, we arrive at this totally mind-blowing realization. And this is the real answer to our question. Imagine this. We want to figure out how to adjust one specific weight way back in an early layer of the network. We've got our formula ready to go, but to actually solve it, we find something crazy. Our calculation for this early layer depends on the results from the layers that come after it. I mean, we literally cannot find the answer for this early layer until we've already calculated the answers for the later layers. It's a total dependency. And this creates this unbreakable chain of dependency that flows backwards through the entire network. To update layer 2, you need the answers from layer 3. To update layer 1, you need the answers from layer 2. See? This isn't some clever shortcut or a programming trick. It's a fundamental mathematical necessity. The calculation has to start at the very end and work its way to the beginning. And that right there, that is the crucial point. This computational requirement, this mandatory flow from the end to the beginning, that is what puts the back in backpropagation. It's not a metaphor, it's a literal description of how the math forces us to do the calculation. Okay, so we've cracked the mystery. Now let's just zoom out for a second and look at the bigger picture here. So you see, backpropagation isn't just some clever branding. It is the fundamental engine that drives all of deep learning. It's this beautiful, elegant process where we use the chain rule to send the error signal from the finish line all the way back to the start, telling every single weight exactly how it needs to change to help the network get better. And why does this all matter so much? Well, because this super efficient, backwards flowing process is the only reason we can train the massive, complex models we have today. It's what allows them to adjust millions, heck, billions of weights, all in a coordinated dance and learn to do the incredible things they do. And this whole thing, it just brilliantly illustrates a really powerful idea that goes way beyond neural networks, right? Sometimes, the smartest way to solve a really complex problem is to start at the end and work your way backwards. Thanks for digging into this with me today.